My name is Daniel Farewell. I'm on the conference board and have a particular interest in the theory and methods component of the program. So it's my special pleasure to introduce to you today Professor Marloes Maathuis. So Marloes is originally from the Netherlands, but did her PhD at the University of Washington in Seattle, and then subsequently has taken up positions at ETH in Zurich, where she's now a full professor. She's currently associate editor on journals including the Annals of Statistics, the Scandinavian Journal of Statistics, and also Biometrica. From that list, I deduced two things. First is that she's an extremely capable mathematician, and the second is that she must also be extremely efficient. The perhaps more relevant for today, though, is that she's also proven herself to be a very gifted and deep and innovative thinker in this new and exciting and challenging world of causal inference. And I'm very much looking forward to her talk on the subject of causality. Marloes.
So I will talk about causality today. And first I only had this title, Causality, but then I decided to make some kind of subtitle to give you a little bit more of an idea of what I'm going to talk about, and that's using covariate adjustment to estimate total effects. And this is based on joint work with several people, in particular Ben Froh, Markus Kalisch, Pritam Nendi, Emma Perkovic, Johannes Texter, and others. Okay, so I would like to start with a very simple example to kind of define the types of problems I'm interested in and also to define some of the terminology. So suppose we have some hypothetical data on a rehabilitation program for prisoners. And we see there were 500 prisoners who participated in the program, and 100 of those got rearrested within, say, a year. And so that's a rearrest rate of 20%. And then we had 1,000 people who did not participate in the program, and 500 of those got rearrested, so that's a rearrest rate of 50%. And now we can ask several questions based on these data. For example, we can ask ourselves, can we predict whether a prisoner will be rearrested based on the fact that he did or did not participate in the program? Or we can ask ourselves, we see here a difference in rearrest rates. This is show, not really, right? Yes, well, over there. Is this due to the program? Or is this maybe due to some other factors? Or we can also try to predict what would be the rearrest rate if this program were compulsory for all the prisoners. And now these are kind of different types of questions. The first question is a classical prediction or classification problem. And it can be very useful, for example, if you want to decide about a possible parole of a prisoner. So here we're just interested, basically, is there some association between participation in the program and recidivism? And in certain cases, that's a very important problem, but I will focus on problems like questions 2 and 3. And those are of a causal nature. And they are of a causal nature because the second one is about the mechanism behind the data. So we don't just want to know, is there an association between participation in the program and recidivism, but is this a causal relationship? And the third one maybe looks like a prediction problem, but it's not a standard prediction problem because it's a prediction problem in a changed system, namely in a system where we would make this program compulsory for all the prisoners. And in order to make such a prediction, we need to understand the causal mechanisms. So now maybe we can wonder, what questions can we answer based on these data that I have? And there, well, that's a kind of a badly posed question or a poorly posed question because I haven't told you how these data were collected, right? So if the people could choose themselves whether or not they wanted to participate in the program, then it's so-called observational data, and then we can easily answer question 1. But we cannot easily answer questions 2 and 3. For example, if you look at question 2, right, we see this difference in rearrest rate, and we want to know if this is due to the program. But if the people are allowed to choose themselves whether or not they participate, there are self-selected subgroups, and the people who choose to participate may be different in many respects from the people who choose not to participate. For example, types of crime they committed, intrinsic motivation to better their lives, etc. And we don't know whether any of these other factors or the program or a mix of those caused this difference in rearrest rate that we saw. Similarly, we cannot just say that the rearrest rate, if the program were made compulsory, would be 20%, because again, this 20% is from a self-selected subgroup and is not representative for the whole population of prisoners. So in order to answer the second and the third questions, it's best to have randomized participation. So in this case, you can imagine rolling a die for each prisoner. If the outcome is 1 or 2, you say the person has to participate and otherwise not. Then, because of this randomization, when we assign the prisoners to these two groups, it's very unlikely that all the motivated prisoners end up in one group, right? This will even out over the two groups. And this will be the same for all possible factors that could affect recidivism. So now the groups are comparable, and we can say the only difference between the group is participation in the program, and so this difference in rearrest rate is due to the program. Okay, so I am interested in answering these types of causal questions, like the questions of like number 2 and 3. And again, they are about the mechanism behind the data or about predictions after making some new outside intervention to the system. I'm interested in these questions because I think they're very fundamental. I don't know, as humans, we are kind of trying to understand the world, and often that means understanding causal relationships. So here are some examples. The smoking caused lung cancer is a very classical example. Can we estimate gene regulatory networks? That's important now in systems biology. Does discrimination play a role in hiring decisions? Or can we predict maybe economic growth under different new tax policies that we haven't implemented yet? So these first 3 are really about the mechanism behind the data, and this is again this prediction in a changed system. So as I said before, it's best to have randomized controlled experiments in order to answer these questions. But these experiments are often expensive, time-consuming, sometimes unethical or not possible. So for example, for smoking, it was thought pretty early on that smoking might be dangerous, and as soon as you think that, it's no longer ethical to randomize people to a smoking treatment. Also, people don't accept to be randomized to a smoking or a non-smoking treatment. So I want to look at, can we answer these causal questions from observational data? Because observational data is widely available, it's generally cheaper, etc. And the goal is not to replace randomized controlled experiments at all. I think my goal is more to use the observational data we have in the best possible way that generates hypotheses that we can then validate in randomized controlled experiments. Okay, so if we're talking about estimating total effects or total causal effects, we first need to define what I actually mean by that, right? And for that we need some notation, and I will use, so there are different schools in causality, and I will kind of follow more the Pearl school here. So I will use his do operator, and this notation do x is a simply means that we set the variable x to the value a by some outside intervention uniformly over the entire population. So it's a mathematical notation for doing an imaginary intervention, basically. So let's just look at this in the prisoner example. So if y is a binary variable indicating whether the prisoner got rearrested or not, and x is a binary variable indicating whether the prisoner participated or not, then we can, for example, look at this quantity, the expected value of y given do x is 1. So do x is 1 just means that we imagine making this program compulsory for all the prisoners. We force all the prisoners to participate. And then we look at the expected value of y. So this would then be the rearrest rate if the program were compulsory for all the prisoners. This is very different than the usual conditional expectation, which would in this case be the rearrest rate among the people who choose to participate. And now, because we have this mathematical notation of interventions, we can easily define causal effects. Because a causal effect of x and how can you think about a causal effect of x on y? Well, you look at the expected value of y under interventions on x where you set x at different values. So you can set it one time at maybe the value a plus 1, another time at the value a. And if the expected value of y is the same in both cases, then we know that x has no effect on the mean of y, right? And the larger this difference is, the larger we will say that the causal effect is. So in the prisoner's example, this would be the rearrest rate among, if the program were compulsory for all the prisoners, minus the rearrest rate if the program is abolished and no one can participate. Right? And that's a fair comparison, and that can be used as a measure of a causal effect of the program. This is again very different than this contrast that you maybe might naively use, which would be the rearrest rate among the people who choose to participate minus the rearrest rate among the people who choose not to participate. Okay, so now how do we get from observational data to estimating causal effects? And I like to think of it kind of in this way, that we have different worlds. So we have an observational world, and then we have an interventional world. Or basically, we have lots of interventional worlds. Maybe for each experiment that we could do, there could be an interventional world. So in the observational world, we have observational data. From that, we can estimate some densities, and we can do prediction or classification. And that involves like regular conditional expectations, like the conditional expectation of x or y given x. And then we can have an experimental world where we did some kind of experiment, we get experimental data. From that we can also estimate densities, which I will call post-intervention densities, because they happen after making an intervention to the system, this experiment. And then we can make causal predictions, and they involve quantities like that involve the do operator. And now what we want is, I want to start from this observational data over here, and I want to go to the causal predictions or quantities that involve this do operator, so that I can define causal effects. And the way I see this is as some kind of extrapolation problem. So we see this one world, we see the observational world, and we want to extrapolate what would happen under a certain intervention. And in order to make such an extrapolation, we need a causal assumption. Because otherwise there's no way we can get to this other world that we haven't seen yet. And one assumption that's often made is that the data are generated from a known directed acyclic graph, or a DAG. So I would now like to explain a little bit what this DAG assumption means. I will do this with a so-called linear structural equation model. So let's go just through this step by step. So this is a DAG, so each variable is a node. There are directed edges between the nodes, and there are no cycles, no directed cycles. I also put edge weights here along the edges, and they tell me how I can generate data from this graph. So you can really think of this as kind of representing the data generating mechanism. And to make it very explicit, I've just written the R code here that you could use to generate data from the graph. So n is the sample size. I set it very large, 100,000, so we don't have to worry much about sampling error. Then I make a big matrix epsilon, which is 100,000 rows and 7 columns. 1 column for each of the variables, and 1 row for each sample that we're going to generate. And then I generate the variables one by one, where each variable is generated as a linear function of its parents plus noise. So for example, Z5 doesn't have any parents, it doesn't have any incoming edges, so I just set it equal to the first noise column. And then the X has one parent, namely Z5, with edge weight 1, so I say X is 1 times Z5 plus the second noise column. And like this we continue, so Z1 is going to be 0.8 times X plus noise. And for example, Y has 2 incoming edges. So Y is going to be 2 times Z1 plus 1 times Z5 plus a noise column again. Okay, now what is special about this model? There is one key assumption. So each of these equations here are called structural equations because they tell me how to generate this variable. And the key assumption is that each of these structural equations is autonomous, meaning that I can change one of these structural equations without changing any of the other ones. And this is the assumption that allows me to extrapolate from this observational world to this interventional world, because it tells me many things will remain the same. only the variable that you intervene on, only that generating mechanism is going to change. All the other generating mechanisms remain as they were. So this is where the DAG assumption comes in, and we will see later on that this allows us to go from observational densities to these post-intervention densities. But first, to make it explicit again, we can easily simulate now from some kind of hypothetical intervention. So if I want to know what happens to this system under this do intervention where I said do x is a, then what do? I keep everything as it was before except for this line that generates x. So before that was over here, z5 plus noise. And now we say, well, I make an outside intervention. It no longer depends on z5 or on noise. I just set it equal to a. And this is a long vector of a's, 100,000 a's, basically. So uniformly over the entire population, I set it equal to a. All the other generating mechanisms remain as they were. So their values don't remain as they were, right? So z1 depends on x. So if I change x, the marginal distribution of z1 will change. But the conditional distribution of z1 given x will remain the same. This generating mechanism remains the same. Okay, so now I could simulate changing this value of a that I take and look at this contrast as we discussed before in order to define a causal effect. But in a linear system, I actually don't need to do that, and I can just look at the directed paths from x to y, and I multiply the edge weights along each path, and I sum up over all the directed paths that there may be. So in this case, there's only one directed path over here, and the total effect of x on y is 0.8 times 2, which is 1.6. So you can also get that if you do the simulation, as I explained before, but there is a kind of a shortcut to just get this 1.6 out immediately. And now, what I would like to think about is now suppose that we know this DAG, but I suppose that we don't know these edge weights anymore. And now I want to see, can I estimate the effect of x on y using some kind of regression? So in particular, I want to regress y on x and maybe some other variables. And then I want to look at the coefficient of x, and I would like this to be an estimate of 1.6. And then the question is, what variables should we adjust for or should we not adjust for? Like, what variables are we going to put in the model? So maybe we can do like a small interactive thing now. And so who thinks we should put z1 into the model? Okay, no one. Who thinks we should put z5 into the model? Okay, a few. Very good. Who thinks we can use z2 if we want to? No one. 1, 2. Very good. Who thinks we can use z3 if we would like to? No one, right? So let's see. So we can easily just do these regressions, right? So I just do linear model y on x, and sometimes I add some other variables, and each time I look at the second coefficient, because the first one is the intercept and the second one is the coefficient of x. And if I don't include any other variables in the model, I get an estimate of 2.1, basically. And so this is biased for the effect that I'm interested in, and that's due to this confounding path here that goes through z5. So if I add z5 to the model, then I'm doing much better, and I get an estimate of 1.6. So people still had a kind of a good intuition. So it's also not a good idea to include z1, so that was good. It's a good idea to include z5. Then I think where the intuition is often less clear is about these other variables here at the bottom. So for a long time I thought myself that, well, these are not needed, but it wouldn't hurt if you include them. Right? Because it seems they are not on a confounding path, they're not on a causal path, so maybe it's not super efficient, but maybe you can use them. But it's not the case. So z2 you can use, so we see that here. If I put it in the model, I still get an estimate of 1.6. But if I include z3 instead of z2, then I suddenly get a bias of 0.8. Sometimes people also think, well, I throw in all the variables that I measured or all the variables correlated to x and y, so I've done that here, and then we get an estimate of 0. So it's worth kind of thinking carefully about what variables you want to put into your model. And this is not sampling error, this is, these are really inconsistent estimates, right? So this 0.8 will remain 0.8, also if I increase to 1 million data points. Okay, there is one other thing that I would like to kind of highlight that can also go wrong with covariate adjustment. And that's called sometimes the idea of doing some kind of mutual adjustment, or the table 2 fallacy. So what's that? So suppose that we want to estimate the total effect of x on y, and we have observational data, and we know with some kind of tools that S is a valid adjustment set. So now we can regress y on x and these variables in S, and then the coefficient of x in this regression measures the total effect that I'm interested in, the effect of x on y. So far all is fine. But now what often happens is that people present this whole multiple regression analysis in a table. Often this is the second table in the paper, because the first table kind of summarizes the data, and the second table is the multiple regression analysis. And then also the coefficients that correspond to these variables in S are implicitly or explicitly interpreted as estimates of a causal effect of that variable on y. And that is not correct. So there's a nice paper by Westreich and Greenland where they discuss this, and they give this example as one case where this goes wrong. So here people are interested in the use of psychotropics, so that's the y variable, and their x variable that they're mostly interested in is work-related violence, and then they put in lots of covariates into this model that they adjust for. So, I don't know, there's several things you can say about this analysis, but let's focus on this mutual adjustment problem. So let's suppose that this is a valid adjustment set, and that this model is also appropriate. Then this 1.38 is a cause-specific hazard ratio. But this whole column is interpreted as cause-specific hazard ratios, right? So they also kind of, it looks like this 1.41 is a cause-specific hazard ratio of gender on psychotropic use, and similar for all the other ones. And this is not a correct interpretation in general. So to show you a very simple example, so we have here a weighted DAG again, and we see here we're interested in the effect of x on y. There is a directed edge here with weight 1.5, and then there's another path with edges 2 and 3. So the total effect of x on y is 7.5 in this case. Right? 2 times 3 plus 1.5. Then there is one confounding path over here, so we need to adjust for z1 in order to get rid of that. There's also another path over here, and that is blocked as long as we don't take z3 in the model. So in this case, we don't want to include z3, so it's clear we need to run this regression, y on x plus z1. And indeed, if we do that, we see that the coefficient of x is an estimate of 7.5, as we want. And we also get a coefficient of z1, which is an estimate of 1 in this case. And this is not the total effect of z1 on y, right? Because we see here the total effect of z1 on y. Well, we have this directed edge with weight 1. Then we have this one here, 2 times 1.5, which is 3. And then we have 2 times 2 times 3, which is 12. So in total, we get 16, I think, for the total effect of z1 on y. And that's very different than this 1, right? So in this case, it happens to be that this is the direct effect of z1 on y, but that also doesn't need to be the case. So sometimes it doesn't have any causal interpretation at all. Okay, so I hope that although it seems like covariate adjustment is something you learn in your intro regression class, and it's used all over the place, I think there are kind of common misconceptions that still exist, and therefore I would like to discuss now how can you select on more formal grounds what kind of variables you put into your model. So the setup is that we're given IID observational data and a causal DAG, and the goal is to identify this post-intervention density of y after intervening on x using covariate adjustment. And so now this is the slide with the most formulas, but just to kind of show you, go away a little bit from these examples, right? So the criteria I'm going to give for these covariate adjustment don't require a linear SEM or something like that, right? And all the examples have been that so far, so this is just to show you that it's more general than that. So how do you make it more general? Well, you can connect a probability density F to a causal DAG by requiring certain factorization formulas. So let's first say that, so you want that this equation holds, right? So if we first take X to be the empty set, then we simply want that the joint density of all the variables factorizes as the product of the conditional densities of each variable given its parents. And now we don't only want that, we also want that if we intervene on, say, one variable, then we want that the post-intervention density of the remaining variables after intervening on one of them still can be written as this factorization where we leave out the variable that we intervened on, right? So this product is now not over all variables anymore, it's over all variables that we didn't intervene on. So this is very similar to the simulation example in the beginning where I said this do X is A through to in a simulation. So we say all the conditional distributions of the nodes that I didn't intervene on remain the same, and only the one that I intervened on is changed. And this one drops out of this factorization formula, and I just evaluate this at this value X is A. So this is again the kind of the assumption that allows us to extrapolate. So we say the conditional distributions remain the same for all the variables we don't intervene on, only the one that we intervene on, they change and they get the value that we set by intervention. Okay, what do we then say is an adjustment set? Well, we say that S is an adjustment set relative to variables X and Y in a DAG if for any F that's any density that's compatible with this DAG in this way that we have defined here, this post-intervention density of Y given do X can be written in this specific way. So what is most important here is on the left-hand side we have this post-intervention density that involves the do operator. That is what we need in order to get causal effects out in the end. On the right-hand side we have regular conditional densities, right? And that's what we mean by identifiable, because those are densities that you could estimate from data. Or that you could know if you would know the true joint distribution, you would also know these densities. And for covariate adjustment, we also require that they appear in this specific form over here. But this form is now not so important, and then one can easily show that if you have a linear system, then this simplifies, and indeed you get that the total effect of X on Y is simply the coefficient of X in this linear regression of Y on X plus S. Okay, so now how can we find sets S that we can use in this regression, right? So in general you would say, how can we find sets S that satisfy this, this requirement here? But if you can just think about linear systems, and then you can just think about what sets S can I use in order to do this regression and get the right coefficient of in front of my X, basically. And then there's a very well-known graphical criterion due to Pearl already quite a while back. That's called the backdoor criterion, and that's sufficient for adjustment. Then more recently, people developed a necessary and sufficient criterion for adjustment. That's due to Spitzer and others. So on this slide, I am just kind of showing you this adjustment criterion, not so that you can parse this completely, but to give you an idea of the flavor of how such a criterion looks like. So we say that S satisfies the adjustment criterion relative to X, Y in a DAG if no element in this set is a descendant of any node other than a node in X that lies on a proper causal path from X to Y. Right? So there's some terminology, I won't define everything, but you can think of a directed path from X to Y. And you want this set S to block all the proper non-causal paths from X to Y. And non-causal paths are defined as paths that are not directed towards Y. And then one can show a theorem that S is an adjustment set relative to X, Y in this causal DAG, if and only if it satisfies these graphical criteria. So this exactly characterizes what sets S you can use. So just to go back to this example to kind of illustrate this, we see here this path from X to Z5 to Y is a non-causal path that needs to be blocked, so we have to take Z5. Then we have a causal path here from x to z1 to y, and we cannot take any nodes on this causal path, nor descendants of nodes on the causal path, except for nodes that are only descendants of x. So that tells us we cannot use z1, z3, and z4, and due to this kind of funny thing here, we are allowed to take z2. And so we can easily see that the only valid adjustment sets in this example are z5 or z2 and z5 together. Okay, so let me see how I'm doing with time. So let's maybe summarize what I've done so far. So I think there is a lot of common folklore about covariate adjustment. So often it is kind of thought that the more variables you put into a model, the more you are controlling and the better it is. So that's not the case. Adjusting for all variables related to x and y is also in general not a good idea. Sometimes it is thought that adjusting for pretreatment variables, so everything that comes before x in the causal order, is always safe. So that's also not the case. You can induce bias by adjusting for certain pretreatment variables as well. Sometimes it's thought that descendants of x are always bad and you can never use them. Well, that's also not the case, as we saw with this z2 variable here that can be used. And then there is this idea of mutual adjustment that in general does not work. So what you want to do instead? Well, I think one should carefully define the research question that one is interested in. So I think one should declare if you're interested in a causal question or not, right? So quite often in regression analysis, people talk about effects, and it's not so clear if they just mean some kind of association or if they mean a causal effect. So I think we should be kind of brave and say either we do causal effects or we don't, but clearly say what we're doing. And then also, in this talk, I focus on total causal effects, but there are other causal effects that you might be interested in, like direct causal effects or indirect causal effects. So one should also think carefully about what is actually the effect that one is interested in. And then, once you've done that and you're interested in a causal question, then I think it's very helpful to draw a causal DAG and to use graphical criteria to decide what variables you put into your model. There are several extensions that I won't talk about here. So in the examples, I've always focused on a single x variable and a single y variable, but the results actually hold for sets of x variables and sets of y variables. So you can think about joint interventions on several variables at once. So for example, a double or a triple gene knockout that you would like to predict. Also, I have only focused on defining the sets that basically give me a consistent estimate of the causal effect that I'm interested in. But among all those valid adjustment sets, some of them are more statistically efficient than others. And we also have some results towards choosing sets that are statistically efficient. Okay, so now you can maybe think, well, this is all nice, but in many of my applications, I don't know this DAG, right? So what am I going to do in that case? Well, I think that's a valid kind of complaint. There are situations where, due to time ordering or background knowledge, you can draw a DAG reasonably well, but there are certainly also cases where it's hard to do that. So what can you do in this case? Well, one approach, I think, is to just hypothesize possible DAGs that you think could have generated your data. Then if you draw these DAGs, you formalize the causal assumptions that you're making, and you can also discuss these causal assumptions with colleagues. You can then, for each hypothesized DAG, determine appropriate adjustment sets and compute the corresponding effect that you're interested in. This also allows then sensitivity analysis, so you can see how much this causal effect changes for the different DAGs that you have drawn, and you can have an informed discussion, right? Because if you don't do this way, then what sometimes happens is, well, people just say, well, I did this regression analysis with these variables, and someone else says, well, I used slightly different variables, and you get different estimates out, and then how are you going to decide which estimate is better or more appropriate? Right? So I think doing it this way kind of formalizes this discussion, and then you can really argue about which edges you believe should be in this DAG or not. Another approach is to try to learn the DAG from data. And this might be a bit surprising that this works, but under certain assumptions, you can get information about the DAGs that could have generated your data. And you're not always able to identify the DAG uniquely. Sometimes, or in general, you get an equivalence class of DAGs that could have generated your data. So there is a whole field that's kind of in this called causal structure learning, and it can be kind of roughly split into, well, it can be split in many ways, but one way to split it is to say, well, there are methods that assume there are no latent variables. So you measured all the variables that are important to your system, and then there are different algorithms that you can use, and they give you a certain graphical object out that represents this equivalence class of DAGs. There are also methods that allow arbitrarily many latent variables to be there, and even under that very weak assumption, right, you can still learn something about the causal structure. And you get a different graphical object out that again represents lots of DAGs that could have generated your data. So now you can wonder, well, okay, if I can learn such an equivalence class of DAGs, can I still maybe find adjustment sets that work for all the DAGs in this equivalence class that could have generated my data? So here is an example of such a CP DAG, which represents a Markov equivalence class of DAGs. And this is a partially directed graph. So you have some edges that are oriented. These are the black ones. And they are oriented like that in all the DAGs in the Markov equivalence class. And then there's also these blue edges with circle marks, and they indicate that we don't know the orientation of those edges. So in this case, this CP DAG represents 3 DAGs, the ones given over here. And in this case, one can quite easily see that there is no adjustment set that works for all of them. Right? Because if we look at the first one and we're interested in the effect of x on y, then, well, we have 2 causal paths here that we don't want to disturb, so we don't want to use Z1 nor Z2. In the second one, I have a confounding path here and a causal path at the bottom. So here I need to adjust for Z1 and I cannot adjust for Z2, right? And in the last one, it's the other way around. I have the causal path here and the confounding path here. So here I would take Z2 and I am not allowed to take Z1. So I get different adjustment sets in all of these DAGs, and I cannot just from this graphical object here read an adjustment set that works for all of them. In some cases, you can do that. So here's another example of a CP DAG. And I've just drawn only 2 of the DAGs in the Markov equivalence class. There are more than that. But one can show that the set AZ, in this case, is an adjustment set, a valid adjustment set in any of these DAGs. And we have developed methods that allow you to directly from this CP DAG, or also from a PAG, to read off if there is an adjustment set that works for all the DAGs in its equivalence class, and if so, what adjustment sets you can use. So here is kind of an overview of work in this area. So here there are columns with a different kind of graph object. So the DAGs we talked about a lot. The MAGs I haven't mentioned before, but these are like DAGs with latent variables. And then the CP DAGs is a Markov equivalence class of DAGs, and a PAG is an equivalence class of these MAGs. So basically the important thing is maybe the CP DAGs and PAGs can be learned under some assumptions from observational data. So if we look here, the black check mark indicates that the criterion is sufficient, and the blue ones indicate it's necessary and sufficient. And we see that, well, we had the Bechdel criterion for DAGs from Pearl. Then this was made into a necessary and sufficient criterion by Spitzer et al. Then this was generalized to MAGs by van der Zande et al. Then with Diego Colombo, we generalized the Bechdel criterion to all these different graph types. And with Emma Perkovic, we generalized this adjustment criterion to all the graph types. And here this little star means that we also adapted this to CP DAGs where you can incorporate background knowledge that you might have from the system. Okay, so this is kind of good. So these, in the CP DAG and the PAG and the MAG case, we don't always get a valid adjustment set out, right? There might be cases like the one example I showed that it simply says, no, there's no adjustment set. So now the question is, what do you do in those cases? And there I think it is helpful to kind of go away from this identifiability, and then we kind of develop this approach which we called IDA. And a schematic view is kind of given here. So you start with the observational data, then you apply some kind of causal structure learning algorithm like PC or GES or whatever favorite algorithm you have. You get an estimated CP DAG, and then you list all the DAGs in the Markov equivalence class of this CP DAG. And if your assumptions were correct, then one of these DAGs generated your data, but you don't know which one it was. Right? So what we do is we just determine a valid adjustment set for each of these DAGs, and one can easily show that you can always take the parents of the X variable as a valid adjustment set. So that's what I've done here. So I take the parent set of X in this first DAG or in all the other DAGs. Then you can run the adjusted regression, adjusting for this parent set, and obtain an estimate of the causal effect corresponding to each of these M DAGs. And then again, under your assumption, one of these estimates the true effect that you're interested in, but you don't know which one it is. But this multi-set still gives you some information, right? So you can take the minimum value, the maximum value, or what we often do is we take the minimum absolute value of all these estimates, right? And if that is different from 0, then at least we have strong indication that there is a causal effect going on. So, but in general, this multi-set allows you to get bounds on the causal effect that you're interested in. Okay, so we have kind of developed this a while back in 2009 and 2010. Recently, this has been extended to the setting with latent variables by Daniel Malinsky and Peter Spertis. And we have done some recent work with Benjamin Froh, where we combined it with a causal structure learning method that allows some latent variables. Because this division into methods that assume no latent variables or arbitrarily many is kind of a rough division, right? So, and neither one is maybe optimal. So assuming no latent variables, well, that gives you informative output, but you don't really trust it because this assumption is almost surely violated. Assuming arbitrarily many latent variables, well, you believe in the assumption, but your output that you get with this assumption is quite weak. So we thought, well, we should come up with some method that allows some latent variables. And what we do is we say, well, we allow a few latent variables that affect many of the observed ones. And by doing that, we can kind of account for this effect of the latent variables and take it out and combine it with this IDA method. So just to show you that this can be applied to data, I have this Arabidopsis example where we have 188 samples, 33 genes, so it's gene expression data. And these genes can be divided into 3 groups, 2 pathways, the MVA pathway and the MEP pathway, and they're also mitochondrial genes. And we don't use this information in the analysis, but we will see that it kind of comes out in the end. This is how this plant looks like, and this is how the estimated graphs look like. So here I have the genes on the X and Y axis, and this is a black box here indicates that there is an edge between the 2 corresponding genes in the estimated graph. So here we use the GES algorithm where we allow no latent variables. Here we use a RFCI algorithm where we allow arbitrarily many latent variables. And this is this kind of new LGES method where we allow some latent variables. And you see that comparing these two, we get a much sparser graph in this case by taking out this effect of the latent variables. And then we can combine this with this IDA method. So each of these graphs here represents many DAGs. For each DAG, we can estimate the causal effect and summarize these multisets for all the pairs of genes. So if a value here is very dark, it means that the minimum absolute value of this multiset was large, and if a value is white, then it means that the minimum absolute value was 0. So we see here we get quite of a dense matrix with causal effects estimates, if we look at LVIDA, we get only three black boxes, so 3 times we get a non-zero causal effect, and the red ones are basically NAs, where we cannot say anything, and the white ones are 0. So you see that this is quite conservative. It calls only 3 causal effects in the end. This is maybe quite dense, and here this is somewhat, it's a little bit hard to see, but somewhat less dense than the one over here. And one thing that you notice is there is kind of a white cross in the middle. And the genes here are ordered in terms of there one pathway over here, the other pathway is there, and the mitochondrial genes are in the middle. So by accounting for the latent variables, it seems that in the causal effects that we still find, we find very few that involve these mitochondrial genes. It's a little bit hard to say from this what output is the best. But one thing that is also nice from this LGS approach is that we found one latent variable in this case, and we could interpret it as indicating in which pathway these genes were. So we get kind of an interpretable latent variable that we found. Okay, so let me summarize what we've done. What I think is the most important part is this first part that I discussed. So the last part, I just wanted to show you some of the recent stuff. But I think if you're interested in causal effects, then you should be brave enough to declare that you're doing causal inference. You should specify clearly what kind of causal effect you're interested in. And you should state your causal assumptions. And one easy way to do this is by drawing a DAG, but you can also do it in other ways. And then I think it pays off to use causal methods. For example, graphical criteria for covariate adjustment, or this IDA method, or any other method that are based on causal reasoning. So this, of course, does not replace randomized controlled trials, but I think it uses observational data in a principled way. And also, so one other alternative is maybe that you say, well, correlation is not causation, so I'm not going to make any causal claims about my observational data. And I think that's kind of too bad, right? Because there is a lot of these data around. So I think this is one way to use this data in a kind of principled way. It allows a formal discussion because you can discuss about the different DAGs that you have assumed or you have learned. It allows sensitivity analysis with respect to different DAGs. And if possible, you should always follow up with validation experiments. I would also like to point out that there is open source software that you can use to do this. So 2 R packages that are relevant are PCLC and DAGity, but there are more out there. They include these causal structure learning methods, like PCGES, FCI, RFCI. And we have also implemented our results on adjustment. So what you can do, for example, is you can put in your graph, say what kind of graph it is, if it is a CP DAG or a PAC or whatever, the sets X and Y that you're interested in, and then if you take type as canonical, it will compute one specific adjustment set, and if that set is valid, then of course it's a valid adjustment set. If that set is not valid, then there is no adjustment set that works. So that is a very easy way to find out if there is any adjustment set for the graph that you're giving it. You can also do type as all, and then it gives you all valid adjustment sets. And you can pick ones that you like. And also for a given set S that you're interested in, you can quickly check if it's a valid adjustment set for a certain graph. Also, this DAGity has a web interface that's also quite nice, where you can draw the DAG and see which adjustment sets are valid. So that's it. Thank you very much.